So we ran short of class time a little bit, so I wanted to make y'all a quick video to kind of keep explaining the chairs and to do a few examples. Hopefully y'all have had a chance to do the examples at the end of your notes and you can follow along. So just to kind of clarify, we were looking at the models in class, but they're small, so in case you couldn't see in the back, I wanted to kind of reiterate what those should look like. So right here I have what's called the right-handed chair. And so you know with the right-handed chair that the point in the top right is upwards on this side. And so let's correlate this with what it should look like in our 2D space. Remember, a right-handed chair, you're going to draw two parallel lines, the bottom one longer than the top one. You're going to draw a point to match and a point to match at the bottom. Remember that you always number your carbons from the point being carbon number 1 and going around. So 2, 3, 4, 5, 6. And we want to make sure that our models match that. So carbon number 1 is the top right, kind of going up and away. And then your 4 in the middle should be flat when you're holding your model. You'll notice that the one that is behind carbons 2 and 3 you can't really see in the photo, and it's because they're flat or right across carbons 2 and 3. Carbon 4 should be the point down at the bottom, and 5 and 6. Remember that the ones that I have with colored balls in my pictures, those are all of our axial positions. And those are going to have flat lines in our diagrams. So with the axial positions, remember that carbons 1 and 3 have the direct relationship. So the axial position on carbon 1 can interact with the one on carbon number 3. Carbon number 2 can't interact, and so looking at our model here, carbon number 1 is actually across from carbon number 2. These do not have any interaction together. But carbon number 1's axial position is directly across from carbon number 3's axial position, and this can cause some torsional and steric strain. Y'all don't need to be able to draw a Newman of your chairs, but they are directly related. Remember, with a Newman you view down a bond, and so when you have this 1-3 interaction, that's kind of like having an eclipsed Newman. And then off of carbons 1 and 2 here, you'll notice the bond's degree angle here is 60 degrees. They have more of a staggered relationship. Y'all can come into class with the exam with these already pre-built. So you'll notice the reason I have my colored balls on my model like this is because when I set it flat on the table, my 3 axial positions actually touch the table. So let's number this again to match what I have drawn down below. This would be carbon 1, the one pointing up and away. Carbon 2, carbon 3, carbon 4 is your point on the left-hand side pointing down in a right-hand chair. And then 5 and 6 are over here in the back. These 4 in the middle again should be flat when you're holding the model and you're trying to view for stability. And then you have the 2 points that are going up and away from each other. So when you perform a chair flip, you literally hold on to carbon 1 and pull it down in your model. Same thing with carbon number 4. You're going to hold it and pull it up in your model. You're not changing the numbering of the model. The only thing that you're changing is where they are located. So when you do that, it's going to change what your model actually looks like, which I have here. So viewing it from the side, carbon number 1 you can tell on the right hand side is pointing down. Carbon 2 and 3 are pretty much in the same position. Carbon 4 is now the one pointing up, and 5 and 6 again are in the same position. You can see it a little better in this version of the model, but they should be flat. And again, this is the left-handed version of the chair. Let's see if I can do a little better drawing this one. The idea behind it's the same. You draw 2 flat parallel lines. You draw a point pointing up, and then you draw a point pointing down. Ooh, it's a little rough. Alright, and so carbon number 1 is now the down point, 2 and 3 are in the same position, 4 is now upwards, 5 and 6. Now this is a chair flip model, So notice something about the colored balls. All of the colored balls that were in the axial position are now in equatorial positions. Remember, these are the more stable positions. So if I had something in the axial position on carbon 1, when you do a chair flip, you'll move it into the equatorial position, but it'll still be on carbon number 1. Now when I set it flat on the ground, you'll see that what was all the equatorials are now pointing up in the air. They've switched into the axial positions. And same thing's true here. This is the less stable position. So when we start evaluating these for stability, you don't want to have things in that 1-3 diaxial position. You want to maximize the number of groups you have in your equatorial position in general. So let's try a practice problem. These are at the end of your notes. So remember that we can use cis and trans to help us figure out how the groups are related to each other. So this is 1-bromo 3-pentyl cyclohexane. Let's start off by drawing the cyclohexane, which is a 6-membered ring. And I'm going to go ahead and arbitrarily put some numbers in. I find it easier to number first and then put the groups in. That way I know that the groups are on the correct carbon. So on carbon number 1 I should have a bromo group. Now the thing with trans is trans does not tell us which one's a wedge, which one's a hash. So I'm just going to choose the bromo group to be the wedge for now. And then we have the 3-pentyl group. So off of carbon number 3, since bromo is on the wedge and it needs to be trans, that means this one's going to be on the hash. That's 1 carbon, 2, 3, 4, 5. That's the pentyl group. Now whenever you make this into the chair, and we're going to try this in a moment, the bromo would be in the up position and the pentyl group would be in the down position. Up and down has nothing to do until you put it in the chair format with axial or equatorial. Ideally, you would want the pentyl group to end up in the equatorial position because it's the larger group. Let's try this down below. We're going to draw all of them of this particular conformer. So at this one, this is 1,4-dimethyl cyclohexane. So let's draw our 6-membered ring again. Whenever y'all do this on an exam, you always want to number your ring clockwise and make sure that your chair is matching. So in the number 1 position, we want to put a methyl, and on the number 4 position, we want to put a methyl. And so it says to draw the most stable conformer of this and then do a chair flip and to decide if it's cis or trans. You always want to do a chair flip to evaluate the stability. So I'm going to start off with my right-handed chair here. And your chair, the top point should always be number 1, and you always number clockwise. So 1, 2, 3, 4, 5, 6. So let's start with carbon number 1 in the up position, and that puts it in the axial position. Again, ups and downs alternate as you go through. So on carbon number 4, let's also put that in the up position. But if I put them in the up position now, that's going to put it in the equatorial. So ideally, if we're trying to make it the most stable conformation, we want both of these to be in the axial position. Typically, to evaluate stability, we would do a flip in order to decide, well, who's the most stable. But if you can try to remember that what was axial will go equatorial, what was equatorial will go axial, it'll help speed this up. I already know that by doing a flip on this particular example, there's not going to be any changes in the energy stability. The number 1 position down here does move equatorial. He's still up. What was up stays up. But on the carbon number 4 position, what was up stays up. So that up position's axial. So let's see how we could fix this. What we're going to want to do to get the most stable conformation is to have both carbon number 1 down. So now when it's down, that makes it into the equatorial position in carbon 1. And then in carbon 4, we want to keep that where it was. So he's still in the up position. So now they're both equatorial. So that is the most stable version of this. To make the least stable version, we would actually do the flip. And when you do the flip, remember you're going to take carbon number 1 and bring it down, and carbon number 4 and bring it up. And that would put that methyl group in the down position, which would be, because what was down stays down, but it makes it axial. And the carbon number 4 position, what was up stays up. So when he's up, that then is the axial position. So that would be not stable at all. So if we were going to rank these, the most stable is where one's up, one's down on carbon 1 and 4. And then the least stable is this guy here. And then the two in the middle are tied. So these would be ranked 2 and 3. So the ultimate question in this was, is the chair cis or trans? You have to come back to your regular flat cyclohexane structure in order to decide if it's cis or trans. So with carbon number 1, we have it down. Typically with the down position, we're going to treat that as a hash. And then in the carbon number 4 position, we have that in the up, and we're going to use up as the wedge. So think about it for a second. As I have it drawn, what is it? It's a trans molecule, and that correlates to this structure right here. So you always have to kind of switch back and forth. We have to be comfortable with taking the flat version of the cyclohexane and putting it into a chair. We use the chair to decide how many axials and equatorials there are to figure out who's the most or least stable. And then we can come back to the flat version to figure out if it was cis or trans in the first place. We have one more example from our class notes. It's a little bit easier if I go ahead and give y'all the hash or the wedge. And either way, you should always have two structures you're drawing. Your original structure and then the flip. And that's going to help you figure out which one's the more stable. On the previous example, I didn't tell you about the hash and the wedge. That's why we had 4 structures. If you have more than 2 substituents off of here, it'll end up being more than 4 structures. So just kind of keep that in mind. We can get a lot of structures here at once. So luckily with this one, I gave y'all the wedges. Since they're both on a wedge, when we name this is going to end up being the cis version of the molecule. And remember that y'all know how to do nomenclature for all of these. So stop for a second and think, how would you name this? Remember that halogens have higher priority than your alkyl groups. So it's going to end up being carbon number 1. And that's a chloro group. Uh-oh, down here at the bottom we have a branch group. So you want to think about, are you going to name the branch using IUPAC or common nomenclature? I'm going to use common nomenclature with this one. If you use the common nomenclature, that would be tert-butyl. When you write the name itself, you always put the guy that is higher in the alphabet first. It has nothing to do with the numbers. So remember, tert doesn't count in the alphabet nomenclature. So we'd have 3 tert-butyl, 1 chloro, and then cyclohexane. Alright? And then if we were going to do it with the IUPAC version of the nomenclature, remember that we treat branches like a baby parent. We have 2 in the baby parent, so that's ethyl. And then off of carbon number 1, we would have 1,1-dimethyl. So it still keeps it in the cis, but it switches who comes first in the nomenclature. Here we would have 1 chloro, and then when you're doing the branch chain as IUPAC, you give me the primary location, followed by a dash and a parentheses. So we would have 1,1-dimethyl, ethyl, and then our cyclohexane. So we need to be familiar with both versions of nomenclature for the exam. Alright, so the next thing we need to do is figure out the chair. So remember, wedges always mean up, and depending on what carbon it is, an up position might be axial, it might be equatorial. So let's try it. I always start with my right-handed chair, and carbon number 1 is always the up point, and you number it counterclockwise. Sorry, clockwise. So that's carbon 1, 2, 3, 4, 5, 6. So carbon number 1 is the one with the chlorine based on nomenclature. So in the up position, this is where the chlorine would go. Think about it. Which position is that? Did you guess axial? Because that's what it is. And then in carbon number 3, that's also the up position. And I don't have a lot of space on my particular drawing. So think about it on carbon number 3, what position is that? That up position is also axial. As a little side note, remember that the 1, 3 axial positions are the worst. That is the least stable. So both of these groups are interacting, which is what we don't want. So we want to perform a flip, and again, if you can remember, when you do any kind of flip, what was axial becomes equatorial, what was equatorial becomes axial. You can already maybe predict the outcome of this. Both of these axials are going to become equatorial. So the left-handed version of this chair is actually going to be the most stable. So if you think back to our model drawings that we just looked at, you grab carbon number 1 and rotate it down. Carbon 2 and 3 are in the same position. Carbon 4, you grab it, rotate it up, and carbon 5 and 6 are in the same position. So when y'all are doing a flip, what was up stays up, what was down stays down. So in carbon number 1, you can remember what was up stays up, or I think it's easier to remember all axials go to equatorial. So this chlorine now is in the equatorial position. And then carbon number 3, he'll also be in the up position, which is also equatorial. So the left-handed chair is the more stable chair for this particular conformation. I hope this video helps a little bit, and email me with any questions y'all have.